Having trouble unmuting. Seems to be coupled to the PowerPoint slide. Oh, thanks everybody for joining us this morning virtually. Very little different than last year, but I think the remote medias are pretty good, so I hope this will go along fairly smoothly. I'm going to try to. Oh, didn't do it. Just trying to get a laser pointer. Well, what I'm going to talk to you a little bit about this morning is a variety of computational materials and chemical sciences. As introduced, I am from Oak Ridge National Laboratory. Oak Ridge National Laboratory is in East Tennessee, next to the Smoky Mountains. So I hope that you'll be inspired to come visit, or come in intern, or come in postdoc at the lab after you hear some of the things we're working on and some of the concepts that we're putting forth. Just to start off, I want to make sure I thank everybody for attending. I want to thank the National Lab, Oak Ridge National Laboratory, for all the time that has been put together to provide you some of this information. And especially I want to talk a little bit about the Center for Nanophase Material Sciences, which is a user facility. And I'll talk a little bit about some of the approaches and some of the neat things that are going on there. At Oak Ridge, we have a fairly nice, vibrant environment of scientific staff and operations folks. There's about 5,000 people that work at Oak Ridge National Laboratory, which includes postdoc students. Constant stream of visitors. We have 600 visitors a year coming into the Center for Nanophase Material Sciences, including people that are in the National Academy of Sciences. And about every quarter, about every 3 months, we have a Nobel laureate that comes and visits. So it's pretty exciting and fun environment to work in, and I hope that you'll be inspired to take a look at it. Down here at the bottom, there's a few websites for the Center for Nanophase Material Sciences, Oak Ridge National Laboratory. And the last link is to our connection through Oak Ridge Institute of Science and Education, which has a large number of possible ways to come in and receive stipends to visit the Oak Ridge National Laboratory. So I encourage you to take a look at these, and hopefully you can jot those down, or just look up them on Google. The talk I'm going to present today is broken into 2 parts, and basically I'll start off by giving a perspective of why materials and chemistries is important to us and why it matters. I'll drop quickly off into the renaissance that is brought about by nanoscience and nanotechnology, and then I'll give a bunch of details on how we go about modeling and simulating the processes and properties of materials and under this sort of hood. Our goal, of course, is to gain control through understanding, and understanding through control. And you'll understand what I mean by that as I proceed. I'll also show, after we go theoretical concepts, then I'm going to talk about theory. We're not going to go on to programming or modeling at this point, but I think in the next lecture, Jean Michael may take you on a ride on that aspect. I'll show you some results that one can get from these simulation tools that are in part 1, which is the classical domain, and then I'll move into part 2, which is pushing toward new capabilities using high performance computing and data analytics with machine learning to drive feedback and control, as I mentioned up here in the screen box. And finally, if we have time, I'll tell you a few short stories on how you put all this together and work with actual industry and make actual impact into commodities in our daily life. So chemistry and materials, we think they matter a lot. Materials and chemistry depends about all of our technologies, including all the materials that we use in our smart devices, our cell phones, our computers, our cars. Everything is based upon aspects of the materials, including the production of new materials, such as is brought about by catalysis, and also exceptional properties that we get from superconductors. Materials are the fundamental basis of all technologies, in both the functional side, like batteries and capacitors, but also on the structural side, automotive, aerospace, buildings, and roads. We depend on our materials, so we're pretty excited about having leadership in materials and chemistry, because leadership in materials means you're a leader in innovation and technology. Now, as I said, materials matter, and I think Madonna back in 1990 sang this song. We are materials people, and we live in a materials world. And so I thought that was pretty insightful by Madonna to realize that materials are important. Then in this century, Lady Gaga come around and sang this song, ra ra ro ma ma gaga oh la la, which is, if you look at that, it's an interesting set of elements, and we think that maybe that's a novel high entropy solid solution. So even in the entertainment industry, people are singing songs about materials and chemistry. So just wanted to start off saying, we're very happy and excited to be able to work in this field. So nanoscience started in full force, sort of initiated back in 2020 by President Clinton, dubbed the Nanotechnology Initiative. And it really did stimulate a whole new renaissance in technology and discovery. And let me just tell you what happened. So at the beginning, we realized that as you change the size scale of materials down to less than 100 nanometers, versus a bulk where you're looking at them with your eye, the boundaries caused unusual effects. The temperatures for the melting changed, the resistance of electrons moving through them changed, the ability of the materials to introduce new chemistry changed. So that was pretty exciting to recognize that if you could sculpt our materials down in a nanoscale, we could control the properties. And so we started thinking, well, if it could control it really, really precisely from molecular scales all the way down to a single electron scale, then we could start devising and investigating new types of complexity, things like quantum computing, personalized medicine, adaptive and programmable materials. So that was the beginning of the vision for nanoscience and nanotechnology. And we made a lot of progress along each of these vectors, towards the nanomedicine, towards the programmable materials, and also I'll talk a little bit about toward quantum technology, which is another transformative advance that I think will come around probably in your lifetime, for sure. Just a quick example of what we've done recently is there's a lot of interest in sort of taking the excess carbon dioxide that we generate through our fuels that are based upon hydrocarbons, and turning that into a commodity, not necessarily an environmental problem. So CO2 is an environmental problem, but it is also a chemical that we can make use of. So typically, it's difficult to take carbon dioxide and convert it into anything because the CO bonds are very happy and you need to break them. So one has to develop a novel catalyst. So this idea of nano-structuring comes into play. So from a calculation, we know if we can structure a material that have very, very electric field across that, that's like a lightning rod. So at the end of that spike, the electric field would be greatly enhanced, and that would provide energy into any molecule that comes close to that. So the challenge became, how do we make that material in a fashion so that it's scalable and we can use it into a real reactor to convert, to catalytically activate CO2. So that's the goal. Well, we found a process called plasma-enhanced chemical vapor deposition. When we made these huge surface area structures, and if you look at these things at the apex, you see these spikes. So that's exactly what we wanted to do from the theoretical calculations that said if we could do that, we could enhance the conversion of things like carbon dioxide or nitrogen through a reduction process. Experimentally, we were able to put this into an actual reactor, feed in carbon dioxide out of the air, and this is concentrated carbon dioxide. This carbon dioxide reacts with the nanospikes, which is enhanced electric field. It couples and produces immediately in single step ethanol. So we take carbon dioxide, put it into this electrochemical catalytic cell because of these carbon nanospike materials, and produce ethanol. So we dubbed this carbon dioxide to beer project, and it was one of the most efficient processes that was enabled through nanostructuring materials. And this is not possible to do with other types of materials, so this is pretty novel. And likewise, this electrochemical activation that is enabled through this electric field effect is general. So any electrochemical reduction can can take advantage of this new material. So carbon nanostructuring really does enable novel processes. And the last thing I want to mention about this is these spikes are made of carbon. So it's not taking some of our precious metals and utilizing non-renewable sources. So that's a really big deal and pretty exciting. So, you know, sometimes you see these things and you go, well, I didn't think that would happen, right? You know, that's not what I thought would happen. For example, you know, the bear that's polar is dissolving in water. Polar likes polar, right? So one needs to sort of back away sometimes and say, well, what happens? You know, how did it do that? Now, we fully understood what happened with those carbon nanospikes, but often at the beginning we don't. So this comes to the point of where theory of modeling simulation is incredibly important. It provides a foundation to develop the understanding of what happened. You know, you put A together with B, and all of a sudden you got Z. You know, you expected to get C, and you say, "Oh, it's a miracle." Well, it's not a miracle. The laws of physics are laws of physics, and laws of chemistry are laws of chemistry, and things happen for a reason. To understand them, you need to back off and do some simulation. So, theory of modeling simulation, and now in this decade, a large amount of data. It has a natural integration with our high-performance computing capabilities. Typically, what we're doing is taking the equations of theoretical physics or chemistry and putting them on a computer and solving them. They're intractable to solve otherwise, but our high-performance computing provides us a means to solve those theoretical equations. And from that solution, we're able to develop a real understanding of what really happened. The electric field provided a force to the molecule that weakened the chemical bond that allowed it to dissociate, for example. And at some stage, our methods and our calculations and our approximations to solve equations become accurate enough that they provide ways of reliably predicting new phenomena and new materials. So that's the basic concept, and this is all founded within theoretical constructs such as quantum mechanics and classical mechanics, which I'll talk in more detail in a few minutes. Computational material science and chemical sciences spans a huge range of different areas. More recently, areas in quantum materials and quantum computing, you've probably heard of that, such as topological properties and unusual magnetic properties. These techniques that we discussed can treat these to some extent. Structural materials such as alloys, various composites and structures that are materials that are used in automotive and aerodynamics, as well as buildings and other areas of technology. Polymers and soft materials, self-healing, smart materials. There's a new class of materials that actually can break and reheal themselves. Well, not instantaneously, on a time scale that's fast enough that you don't lose the coherency of the material itself. Energy materials, batteries, energy storage, and nuclear materials. Again, our nuclear sciences is something that's very strong, but you know we need to do a renaissance in our new nuclear power facilities. So these techniques that I'll discuss are applicable to all these areas, and as you can see, it's a broad range of possible technologies and exciting areas that really touch everyday life. So how do we really do that? The way we typically work is that we look at different time and length scales. So time can go up to days or hours, but it also goes down to picoseconds, 10 to the minus 12 seconds. And it spans length scales that are smaller than atoms, such as electrons, all the way up to length scales that are astronomical. So typically what we do is we break our calculations down from the theory into a set of equations that match these length and time scales that are appropriate for what we're trying to study. This is basically the equivalent of an experimental microscope or a spectrometer or a telescope. So that's we dub it a computational microscope spectrometer. I won't talk about the telescope part, but you can generate a computational telescope. It starts at the quantum level, which is electrons and nuclei, moves up to all the atoms, and all the way up to the continuum level. The goal here is to really do these calculations to understand what's going on, not just to get a bunch of numbers. This statement here, compute for numbers, but to procure understanding, was a statement that Walter Kohn, who's a Nobel laureate that is for the density functional theory, said at a conference. So I thought that was very impactful. Compute not for numbers, but to procure understanding. And that's what this is computational material science and chemistry is all about, is to procure understanding of what's going on, as I mentioned before. So a few concepts that you're going to hear, and maybe you already heard, is this set of terms: models, simulations, and theory. Okay. Models are typically just a representation of the material or the process, coordinate system, boundary conditions, the potential energy, forces. The theory is either classical mechanics or quantum mechanics, and typically in computational chemistry and material sciences. And simulation is solving equations that come about once you put them on the computer. So you have to have a model to start with, and then you generate the equations, and then the simulation is solutions to those equations that you got from the theory. And that's where the computational microscope and spectrometer comes into play, the simulation part. So the difference between modeling and simulation, again, modeling is just a physical representation or mathematical idealization of a real problem. Like, for example, a map is a model of a region or a subway. It's just a model. It's not exactly, but it's pretty good, and you can extract information from it. Simulation is solution to that model. So that's sort of the difference between modeling and simulation. And you'll hear many times these referred to in literature as well as in practice. So let's take a look at what we can do. Let's start off with treating systems as a set of atoms, all atoms, and then we'll proceed down in this part one all the way to the continuum level, and then part two we'll go back and say, well, what about if we treat all the electrons, what happens? So the fundamental theory that allows us to look at atoms in a fairly efficient way is basically classical Newtonian physics. Force equals mass times acceleration, which is, I think everybody's heard of. If you write that down in terms of differential equations, you'll get a set of n differential equations that are coupled. And if you could solve those, you would learn the position of all the particles in the system as a function of time and their velocities. So you would be able to say what happens to that system under a given initial condition over time. That's typically the approach of classical trajectories or molecular dynamics simulations. In order to solve those equations, so you need to have, first of all, we're reasonably close. What are the mass of those atoms? And how do those atoms interact with each other? Because we need to take the derivative of that to get the force to put into this equation. So we need that potential of interactions between all those atoms and each other. So that's one of the things that has to be put into these calculations, is that interaction potential. And we need to be able to figure those out. Now, materials and chemicals are pretty diverse. We have things ranging from ionic bonds, which are very different than, say, a typical chemical covalent bond, which is very different than metallic bond, which is different than some of these magnetic systems in these topological quantum systems, which have strong correlations. We need to be able to define all those interactions accurately. So putting together these potentials takes a little bit of effort. Typically, the most common approach to put together a potential is to specify a ball spring bottle. This shows two benzenes, C6H6 interacting with another C6H6. And we can just specify each atom connected to another atom by a bond, and then three atoms connected and interacting through a bend, or four atoms connected and interacting through a torsion. And then there's interactions that are not directly connected, which are called van der Waals or long-range interactions. We can specify potential energy functions for any of those types of interactions: the bonds, the bends, the torsions, and the non-bonded or the van der Waals interactions. And some of the common forms are harmonic oscillators for the bond stretching and the bond bending, and a Fourier series with multiple minima for the torsion, and a Leonard-Jones and Coulomb interactions for the non-bond interaction. So we can write those down, and if we can write those down, we can take the derivatives. It's just the first derivative to put into the Newton's equations of motion. So example of different types of models for these intertonic potentials range from, as I mentioned, the harmonic oscillator, Leonard-Jones. There's Morse potential, which allows chemical reactions to occur. There's Buckingham. These things can be used in the derivatives and the equation that come out of putting these into the Newton's equations. Can be solved for millions to billions of atoms, so pretty large systems. There's multi-body potentials, which are more complicated and more representative of things within the biology or chemistry in general, because they have more interaction terms that treat physical and chemical reality. There's various versions of those, charm, amber, which are very popular in biology and protein folding and enzyme research. United force fields, writing. There's a large number of these, and you can look them up. Typically, the more terms you add into this potential, the more complicated the derivatives are, and therefore the more computer power is required to solve those equations. And that means less number of atoms can be treated typically over a reasonable time scale. But nonetheless, with the computers today, we can do hundreds of thousands to billions of atoms still, even with fairly complicated potentials. Moving forward, there's a class of potentials called reactive potentials. There's one called reax-S, there's Rebo, there's cone potentials. These try to add in real quantum nature to chemistry within a fixed analytical potential. So they're still solving the classical equations of motion, but it adds in a little bit of quantum to treat the chemistry. Those can only be used to study atom numbers of, up to probably 10 to 100,000 atoms. Finally, of course, there's quantum mechanics. You can also solve the equations that allow you to look at where the atoms are and how they move with quantum mechanics, or tight binding methods. Again, these are more accurate and more representative of the quantum world, so fewer atoms can be treated. Although I think there's been some breakthroughs in tight binding, and I'll tell a little bit about that. Anyway, the suite of techniques, the suite of potentials that are available sort of allows us to treat pretty large systems for a fairly long time. Once you have the potential defined, which you can do pretty easily, or you can select a potential from the available potentials. You can do a number of things. I mean, you don't have to immediately solve Newton's equation of motion. You can just solve for the minimum. So if you remember from calculus, if you set the derivative of the function to you find the minimum. So approach, and that approach can do really large systems and find the equilibrium geometries of things such as proteins or other molecules. And it's just a matter of optimizing that potential so that the derivatives are close to zero. So you're doing a gradient descent and finding the minimum. And that'll allow you to look at what type of structure should exist at equilibrium or at a specific temperature. That's called molecular mechanics, and that allows you to find initial structures that are viable and probably exist. Now, once we have a structure, we could say that, we know that force equals mass times acceleration. We could put the derivatives of the potential into the equations and solve them. And that will allow us to map the trajectory over time, or the positions and the velocities of those particles in that system as a function of time. That is the molecular dynamics. And molecular dynamics does just that. It allows you to follow the evolution of whatever system you put down for a given potential over time. It gives you a movie. You can visualize the movie. You can see things moving. And you can follow that and extract quite a lot of information from that. Yeah, the problem, of course, is you want to represent the experimental or the realistic conditions. So you have to actually put some boundary conditions in, a certain temperature, a certain pressure, maybe electric field, maybe there's some mechanical strain and you're looking at mechanical collapses or crack propagation. You need to put those in, and that's pretty easy to do and pretty available. Again, it is a many-body problem, but it's much simpler than the quantum many-body problem, as we'll see later on today. So the basic algorithm for molecular dynamics is to start with some selected positions, and then probably you minimize that using molecular mechanics to get a very stable initial condition. You assign velocities to the atoms after you have defined where the positions are, either from molecular mechanics or some model. And those velocities are usually assigned using the Boltzmann distributions so that you achieve a certain energy or a certain temperature. I think John Michael will tell you more about thermostats on how to control temperatures and pressure, so I'm not going to go over that. Nonetheless, you can specify those and specify the initial velocities of all the particles that you have put into the system. You take the derivatives of those potentials to get the forces, and then you solve the equations of motion that are generated from the, Newton's classical equations using an integrator. I'll tell you a little about an integrator, which allows you to solve those differential equations. You save the positions and the velocities or correlation functions that you generate during the trajectory until you reach whatever time or whatever condition you want and stop the simulation. You can keep track of bond lengths, angles, dihedral, diffusion, structure factors, vibrational frequency, a lot of things you can get if you know where the atoms are and how they're moving over time. So it's a pretty powerful technique. And as I mentioned, if you save it, you can visualize it and you can see a movie. And I'll show you examples of movies that have been extracted from electrodynamic simulations in a few minutes. So some good resources to look at that show some codes that are typically going to be in Fortran, but you can also find them in C and Python also these days are available. This is a good reference down here to get a nice overview of the different algorithms and different approaches. Integrators to solve those equations are diverse. You know, it doesn't have to be a fancy integrator. It just, you know, if you're trying to do simple simulations of just the dynamics of atoms moving in a molecule, I think one can easily use the Verlet algorithm, which is shown here. This one is the central difference. There's also the simplest ones, which is the leapfrog. It works just fine. And there's a variety of other kinds of integrators ranging from ring-encoded gear, predict, and predictor correctors. You know, they all work and they all have a different efficiencies. I think the most efficient one is the Verlet algorithm. So, you know, typically you don't need to worry beyond that for most of the molecular dynamic simulations. Once you have all this down, you need a computer. And tell you a little bit about modern computing. First, I'm going to start with less modern computing over here on the left side. Back in the 1980s, when I was doing my PhD, the best computer we had was something called a VAX 11780. Probably nobody's heard of that, except some older folks. That was really an amazing machine, but you know, we couldn't solve very many equations that in molecular dynamics simulation. We could do maybe 30, 40 atoms because this computer was only running at a kiloflop, about 100 kiloflops. Today, we have progressed up to 100 petaflops, which is, you know, 10 to the 15th. Petaflops 10 to the 15th, kiloflops 10 to the 3rd. So we have progressed by 12 orders of magnitude in our computer power, which means, you know, we can do a lot of equations and solve a lot of equations. So we can treat really good time scales and really realistic length scales today, as opposed to back when we were using the VAX 770. I could do quantum calculations for 3 atoms, 4 atoms. I could do classical molecular dynamics simulations for 20 to 30 atoms, but then it really was not possible to do it beyond. But now we can do hundreds of millions of atoms to billions of atoms in time scales that are representative of experiments because of this incredible progress enabled through Moore's law of going from kiloflops to petaflops. And, you know, next year, exaflops, 10 to the 18th floating point operation per second. That's just incredible. So, we're here today. We're around 320 petaflops, and that's available at Summit and also at various other places, but the work at Oak Ridge is typically on Summit. And next year at Argonne, we'll have the first petaflop machine. And later at Oak Ridge, we'll have another petaflop or exaflop machine. What's beyond this? Exaflop is a lot of compute power. It's not enough to solve everything we want to. There's a lot of thoughts on what's beyond this digital computing age on Newman type approaches. Neuromorphic computing is possible, quantum and mixed accelerated nodes. I'll talk a little bit about quantum because I think it's pretty interesting, but it's just emerging now, but there are some capabilities that one can access. Good news is that all these computing capabilities come with some caveats and complexities, and trying to sort through everything oneself requires too much time. So there's been a huge effort. DOE has put a large amount of funding forward to develop real tools that allows people to develop new capabilities and get the codes running quickly, ranging from programming models to new development tools, extremely efficient math libraries, and that's very important for simulations. Excellent data visualization and a whole ecosystem for the software. And that's independent of whether it's a petaflop machine, exaflop machine, or some earlier version of a smaller machine. This exists and is available in an open source format, so people can access these tools and move fast to get things working in principle. There's also a lot of really excellent software available. I mean, one doesn't have to write their own quantum chemistry or quantum physics code or molecular dynamics or molecular mechanics code from scratch. Now, it's certainly easy enough to do, but when you're trying to tackle a problem that maybe you need to solve in a short time, maybe you just look at some of the existing software that's free and open source. So there's quite a large number of different quantum chemistry codes out there and quantum physics codes out there. Ranging from MWChem, the next version is called MWEX, which will be exascale compatible. There's many-body physics codes that can also do chemistry called quantum Monte Carlo, and that's solving the actual many-body problem, so it's the most accurate possible solutions you can get. Games, which is a quantum chemistry, to various versions of MD and type binding. So these codes exist. These codes have been optimized to run on these high-performance computing systems, as well as other systems, so it's independent of the system. It's meant to be very usable across different formats. Even, I think, MWChem you can run on your cell phone, for example. So it isn't married explicitly to high-performance computing. It's just that those high-performance computing facilities allow you to solve more equations in a faster time scale. As I mentioned, high-performance computing does allow you to do very big things. But even though we're at several hundred petaflops of compute speed, we're still stuck in doing billions and millions of atoms. But the real problem is we can't integrate those equations forever. We can only integrate it for a finite time period. So sometimes if you're looking at aging processes, material that ages over years, you have to do other things to model that. Or if you're trying to understand some quantum effects, you have issues in convergence. And even the biggest digital computer today can't converge some of these things or treat the right time scale. So the time scale is still a problem, even with these big systems. A long time ago, a genius, a Nobel Prize, said, if you want to make a simulation of nature, which is what we're trying to do, right? You better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. I love Feynman. He's actually quite comical sometimes too, but he's always right. So in basically what he's saying, if you could do these things with a quantum computing, you actually could solve some of the problems that might seem intractable. Currently, we do have abilities in this area, and some of the problems that quantum computing can look at are various versions of understanding factoring, which is sometimes encryption, a whole set of capabilities with eigensystems, which is a quantum mechanical problem, quantum chemistry or quantum physics, Also, applications to machine learning, which is I'll talk about in the second part. To date, there's been results shown in high energy physics, materials and chemistry, biology, AI, data analytics, and various other areas of science and technology. So it's moving. You know, it was stagnant for a long time. You know, Shor's algorithm's been around for a while and for factoring numbers. And all of a sudden there's a renaissance in this area because we were able to find materials that actually do have quantum properties and put them into actual functioning bits, which are called qubits, which take advantage of quantum phenomena superposition so that you don't just have a 0 or a 1, but you have a 0, 1 and a 0, 1 at the same time, which allows you to do really amazing computation. Currently, our computing facilities at Oak Ridge National Laboratory offers resources and research capabilities to are evaluating different technologies and generating new technologies in this area. And largely to support the community. So if you're interested in this area, I think there's a great resource at Oak Ridge that you can tap into. It allows you to look at and utilize, once you get a project, various versions of quantum computers that exist today, ranging from the D-Wave, which has 2048 qubits. It's an adiabatic quantum annealing type system. I won't go over what that means, but it allows you to do some things. IBM, which has a 53 qubit system, and Regatta, which has a 31 qubit system. So these resources are actually available through our Oak Ridge Leadership Computing Facility already, and people are using them to solve certain problems. If you're interested in learning more, we just finished the Quantum Computing User Forum, and in October coming up, again, whether it'll be actual physically or virtual, IEEE is having a Quantum Week. And then supercomputing, which is in November, we'll have an international workshop on quantum computing. Again, this is the future of one future swim lane of computing that can get us past the exaflops on certain problems. So it's pretty interesting, pretty exciting, and it can be applied to the problems that we have been talking about in terms of chemistry and material sciences. So I just wanted to mention that. Forgetting what computer we're using doesn't really matter anymore. What kind of questions can we begin to answer? So, you know, we know where the atoms are, we know how they interact, and we can integrate their equations and solve where they are as a function of time and change the initial conditions. So if we can do that, which we can start looking at how the interactions between the atoms and how the correlations of the motions of those atoms dictate how they form structures and what type of properties and what type of chemical processes they allow. So that's a huge thing. So basically, we can simulate on the computer a lot of things that one would do in a laboratory, but because it's on the computer, we can do it in a much more efficient and economical fashion, because these computers are available to the world, and you know, you don't have to buy the computer. That resource is already there. You can study what is the effect of structuring properties due to this confinement, as I mentioned earlier, and we know if you nanostructure things change. You know, we don't know what all changed, but we know that some of the properties change, and we've seen that. You can look at how a molecular ensemble confined to the surface or inside of a pore can connect to the interfacial chemical composition, how that changes separations like water desalination, various other or transport of ions and batteries. So it's a pretty powerful thing that one has access to once you solve these equations on some sort of computing framework. Again, the computing frameworks are not something that one has to buy. Those are available in the DOE facilities. The problem comes, you know, as I mentioned earlier, you know, you got to be careful what you ask of these calculations, because they all have approximations, and we'll go over that a little bit. So let's look at some relevant problems to science and technology. This first example is just an example of a model of the cell wall, which is composed largely of a phospholipid, which is this thing here in the middle. Out here is the aqueous media. That red stuff is mostly water. and this is the cell membrane. And the question is, this cell membrane actually has about 20% of a phosphoryl serine in it, which is also a lipid, which has these blue atoms, which are ammonia ions in it. And the question is, you know, over time, how does that cell wall open up and let stuff through? Because it's pretty impermeable. As you can see, it's isolated to water, and the water's not getting across it. And we want to see over time if adding in certain molecules can manipulate the cell wall to allow transport of nutrients or other things. Some things are not good, as you know, into the cell. But we'd like to understand that process. So we write down the Newton's equation of motion. We specify a potential, like we already talked about. The bonds are specified by harmonic oscillators. The bends are harmonic oscillators. A Fourier series for the torsions, and then Slender-Jones interactions and Coulombs for the non-bonded interactions. Very simple. The number of atoms here are in the millions, so there's a lot of equations, and we put it on one of the supercomputers. And we say, well, what happens as a function of time? And does this thing nucleate these phosphoryl serine molecules to form a pore and regulate the pore actuation to allow nutrients across the cell? So fundamental question, put it on a computer, run the simulation. As you see over time, quickly, these blue pieces of that phosphoryl serine aggregate together, and because they're very attractive, and quickly form a actual pore across this lipid bilayer to allow the nutrients that was in this aqueous solution to pass through and enter in area. So again, this is a very large simulation, and at the end you can see that we actually did form a pore, and that it allowed this nutrients or whatever was in this aqueous media outside the cell to enter inside the cell. So it's an example of being able to study fundamental questions using these classical trajectory approaches or classical molecular dynamics approaches. Another example is a case of trying to understand what happens when you change solvents for other types of molecule. This molecule is a semiconducting polymer, and if you have it in a really bad solvent, it tries to get away from the solvent. It folds up into a really beautifully, tightly packed structure over time. If you have it in a good solvent, it still maximizes the interaction with the solvent and it stays unfolded. So the question is, well, okay, so we know we can control the folding and the structure of this semiconducting polymer by changing the solvent based upon these calculations that are molecular dynamics based. What can that get us? Well, if you can stack these things, these semiconducting polymers into these tight rod-like structures like happens with a given solvent, and we discovered what the solvent needs to be by these simulations, then you have a nice dipolar structure here that allows you to have a very long fluorescence lifetime. If you have it in an unfolded state or picoseconds, but if you fold it up into this nice compact structure because of the interactions it attains, and looks like a single dipole, you can have fluorescent lifetimes that last over an hour. So we just changed a lifetime of a fluorescence emitting molecule from picoseconds to hours. That's amazing, right? And we discovered that through a process of running molecular dynamics simulations and putting different types of solvents to guide that molecule to structures that would enable this sort of phenomenon. So another example of, well, what can you do? And so there's a lot of things you can do. And again, as I mentioned, these things can be quite enabling and guiding new technologies. Another example is the case that we all have heard of graphene. It's the super material of the 21st century. And, you know, making graphene can be done in many ways. And one of the ways we were trying to figure out is how we could make graphene so that we knew exactly what width it was and could always get the exact same width each time, because the width of this thing matters a lot in the properties, especially the semiconducting properties that one gets. And to make a device, you need semiconducting properties, not the metallic properties. So controlling the width of graphene is very important. yet very difficult to do, because when you do the chemical synthesis, you get statistical average of different widths, and that won't work for an actual device. You need a single width. So our idea is like, well, if we could just cut a nanotube along its axis, the width would be determined by the circumference exactly, right? So you just unfold that, and that width of that graphene would be equivalent exactly the circumference of that nanotube. And we know how to make nanotubes in bulk and nanotubes of different sizes. So we could control the width if we could just unzip the nanotubes. Interestingly enough, there's many ways to do that, but one of the ways was discovered by one of the graduate students is that if you just take this nanotube and put it in liquid nitrogen, which is easy to come by, and then stick that into a boiling water, you basically can unzip it. Why does that unzip? So we ran simulations to understand why it can unzip and how well that process can be controlled by using the molecular dynamics simulation. So here on the left is a set of orange hair tubes, and then here's a set of zigzag nanotubes, and inside the walls of this nanotube is liquid nitrogen, which is very cold, around 70 degrees Kelvin. And then we heat it up to boiling water, which is 100 degrees Celsius, and run the simulation to see what happens to this carbon nanotubes, and we can study the process over time. And as you see, very quickly, it unzips. You see the first wall unzips. Later, the second wall unzipped. The inner walls are too strong, but we did unzip it, and we have actually the width of that nanotube exactly as dictated by the circumference. Now the zigzag comes undone. And this has been experimentally validated, and we sort of developed an understanding of the process and how that can be scaled up to generate larger quantities of controlled width nanotube or graphene from carbon nanotubes. Just another example of what you can do. Finally, what happens when you put metals and excite the metals on a surface. This one on the left is on a different surface, and as you change the surface interactions, you can get different structures. And if you understand how the interactions between the surface and the metals on that surface are modulated, you can make any structure, any shape, any wire that you want through just thermal processing. So a lot of things one can do, and using these techniques, and it's pretty exciting, and can directly connect in to real-world applications and real-world technology. Seems like it. So we talked about all-atom and all these things I just mentioned for all-atom simulations using classical molecular dynamics simulations. We can also look into moving to larger length scales. As I mentioned, we look at things in terms of length and time scales. So what if we want to look at things at micrometers and microseconds or millisecond time scales? To do that, we move down our computational microscope spectrometer and apply some other techniques in the area of strain. This is a pretty neat example, and John Michael might talk a little bit more about it later on this afternoon. Understand semiconducting polymers for photovoltaics. So we're making a material that it absorbs light from and converts that light into charge carriers or electrons. And if you have a junction, you can separate the electrons from the holes to generate electricity. So the question was, well, we know some materials that can do that. This material is called poly-3-hexathiophene, shown here, and we need a place where the electrons can go. So we have this donor system, which is the poly-3-hexathiophene, and an acceptor system, which is a C60 system. And we can ask the question, well, what happens over time at different temperatures, and what is the best temperature to apply to this material to generate the right structures so that we can put light in and get electrons out? So that's a really hard problem to do in a lab, because if you want to change the amount of this or the amount of this that you add, or the length of this polymer, you have to do new synthesis and new characterizations every time. So if you could do it all on the computer, that would be a tremendous advance in our ability to develop new photovoltaic systems for technology. So we developed the model. Again, this model is shown here. The white stuff is the polymer, and the blue stuff is this receptor, the C60 molecule. And we said, well, what happens as we run this simulation over time, and what kind of structures can we get, and can we control those structures by changing how much of this we put in versus how much of that, or what the length of this is, or maybe we have to add another molecule in. So this is the largest simulation ever done back in 2016 ever. It was run on the Titan supercomputer. It used 10% of the computer, and it ran over 5 days to generate this movie. As I mentioned earlier, we watched this, collect the data over time, and then we can use the graphics to show the process. So in the right side, you'll see the actual dynamics occur. Initially, it was randomly distributed, and over time, you start to see this nucleation and aggregation of the white molecules, which are the polymers, into domains, and the receptor molecules, which are the C60 molecules, into other domains. The idea is if you can control that separation to within 10 to 20 nanometers, you can get the most efficient generation of electrons from photons in this photovoltaic system. And you can see over time it starts generating these domains that are around 10 to 15 nanometers in length. So this system is a really good system in terms of this material to take electrons, or take photons in a photovoltaic cell and generate electrons. Now that we can validate that this structure is correct by comparing to neutron scattering, we did that. We can now move forward to ask other questions. So, well, let's change the loading ratio. This was 1 to 1. Let's change it 1 to 2. Let's change the length of this polymer. This was a certain molecular weight. We'll change it to a different molecular weight. We'll find the best possible structure that generates the highest efficiency. And then we can go into the laboratory and actually do the experiment. So that's an example of coarse grain simulations. This was about 100 million atom simulation, but it was a coarse grain simulation, and it was calculating time scales on order of 6 microseconds. Other things you can do, we can ask all sorts of questions about other types of lipid bilayers. I told you the phospholipid earlier. This is just a simple lipid, and we've developed ways of monitoring that in real time at time scales and length scales that match actual real cells and experiments. And you can start asking all sorts of questions about formations of RAS and domains and pores that we talked about earlier, and understand especially how adding different things into the media control the formation of these different types of pores and structures. So it's very similar to the case I mentioned earlier with the phospholipid, but it's different lipids. So we can look at lots of different things, ranging from biological questions that are fundamental to physical sciences questions that are fundamental. Nice answers that can compare directly with experiments and feel competent to use those models to start doing other predictions. So we've gone from all atoms. We saw quite a few pretty exciting examples, I think, of what that could do. To coarse grain, again, saw some pretty neat examples. To now moving out to the continuum level. Continuum level allows you to look at a lot of structural materials properties, and there's finite element approaches that are fairly efficient and scale well on computing systems. It allows you to look at anything from material deformation to different types of processing, very high rate, high strain deformation conditions, melting and solidification. You can look at even things as large as cars and batteries. And one of the things that was done early on one of the supercomputers was to use these continuum and finite element models to study the integrity of cars in a crash versus taking the car and crashing it thousands of times. You could use the model, and if the model was accurate enough, which it was, you could use that to understand the collision safety and as for the car mechanical structure, as well as the battery. As we moved into this era of lithium-ion batteries, we want our batteries to be safe. So this allows you to model very, very, very large scales, you know, all the way up to cars and airplanes, and understand some of the processes that lead to mechanical come from you know, mechanical breakage or mechanical other processes. You can put that together with some of the techniques I mentioned before to look at the microstructure all the way up to this car level and look at things such as 3D printing, which is a very hot topic now, and that works quite well, and various other aspects of deforming materials and fibers that are fairly important to our textiles in the industry. So the computational structural materials aspects using these longer length and time scale approaches are also quite enabling and important. Just want to mention that. So far we talked all about classical mechanics. Everything from atoms to coarse grain to continuum level is all based on classical mechanics. But you know, we learned early on in physical chemistry or quantum chemistry that really matter kind of doesn't behave as a particle. It sort of behaves as a wave. So do we need to start over? Do we need to not use classical mechanics and use the fundamental theory of quantum mechanics? Just look at the probability of the positions and time of velocities. Good question. You know, it depends on the length and time scales, as I mentioned earlier. And as we'll show here is a time scale and an energy scale and a length scale that, well, quantum is important, for example. The other ones that we just discussed, which were looking at very large length and time scales and reasonably low energies, we didn't need to worry about it. But here is a case, well, maybe we do. This is just a graphene, again, shown here in the blue, interacting with a beam of hydrogen ions that are going to be accelerated to the graphene. And what we were trying to do is say, well, how much energy transfers from this beam of ions to the surface, and can any of these hydrogen ions stick and form a hydrogenated graphene? That was the question. And on the classical side, we run the simulation and we get a really large amount of energy. As you can see, this deformation of the graphene is pretty extensive. The hydrogen ions all sort of get stuck on the surface, and indeed you can start forming the interactions that are strong enough to actually bond to the surface. Well, if we run the quantum case, so this is sort of the ending of the classical case, again, similar simulations, the energy transfer is tremendously smaller and nothing really sticks to the surface. Everything kind of reflects. A couple of atoms stick. So the classical is overestimating the amount of energy transfer and thus, therefore, the chemistry that can occur in this particular calculation. So quantum does matter, but it doesn't matter for everything, is the caveat. And so again, as I mentioned earlier, we got to be careful with where we apply our particular approaches and make sure that we apply them for the right length and time scales. So the caveat is, well, be careful, and we know that we should be careful. So how do you know where to start? As I mentioned, there's these different approaches. There's the molecular mechanics that just solves for the minimum energy and the potential to give you some structure. That's best for very large systems and systems that do no chemistry. Okay. If you want to do chemistry, you got to move on to other types of approaches. It's molecular dynamics or semi-empirical or ab initio, which are all quantum systems. So there is a guidebook for what methods to be used, when and where, and again, it depends a lot on what the process is, whether it's a chemical process or just a mechanical or physical process, or whether there's actually any chemistry that occurs. So this is available, and we have a lot of experience over 2 or 3 decades on where these approaches can be used to solve real problems. So with that, I sort of finished part 1, and I can stop to get questions, and I'll just open the floor up for questions, and then at 1:30 I'll start part 2, which we'll discuss the details of quantum approaches, what they can do and how we can put those together with classical and machine learning to push the boundaries of new technologies. So I'm not sure. Is there, can anybody just ask a question at any time, or do
I was going to say,
somebody
Dr.
has to?
Sumpter, are you able to see the chat?
No.
Okay,
Oh yeah, I see. Yeah,
yeah, so
interesting.
I was going to
Okay,
say someone asked
I
a
didn't see that
question.
before.
Yeah, no, it's okay. Yeah, they were laughing at your joke. You did. I don't know if you
Oh,
caught that.
yeah. No, you can't. That's a problem with virtual. You don't get to see. I'm glad that they got the joke. Yeah, so the classical force field used in that hydrogen impinging was just a simple inter-Jones and Coulomb interaction. Did somebody ask about that? So it's pretty simple. The graphene was full atom model with the standard potential functions for graphene. And let's see, is there any more questions?
For the carbon nanospike that you had at the beginning,
Yeah.
How do you simulate that kind of structure? How do you make that?
Yeah.
Wise?
So we had excellent electron microscopy techniques that allowed us to see what type of exact structures we could generate through this chemical vapor deposition process with a plasma enhancement. So we zoomed in because we can see every single atom in those structures. So we generated initially it was a simple thing. We just said, well, let's generate a perfect conical carbon structure and see what it does. And then we see the electric field. But to connect with the real experiments, we took the electron microscope and generated a model based upon that, which gives us exact positions of all the atoms in that spike. So it was really very realistically developed based upon the electron microscope. Does that answer your question?
Yeah. And so could you were there absorption spaces inside of the spike as well, or was it just kind of surface?
Yeah, it's not perfect, right? There are defects in these sites. But the very apex of that spike is pristine graphene. It's pretty good. The question is, I mean, there's a lot of questions one can ask. What are the effects of different absorption sites as dictated by missing atoms or other types of atoms? And can that be used to enhance the efficiency of this conversion process? And we're working on that, actually, as it turns out. And at first stage, we did not look at that. We just said, this is perfect, and it's perfect all the way through that spike, and this is what you can get. The interesting thing is, that the process of taking waste CO2 and converting it into ethanol is pretty attractive because, first of all, ethanol can be fuel or for our machines, but it also can be socializing, right? So this technology was exciting enough to industry, and that we got licenses from a company called React Well, which their major product is alcoholic beverages. Turns out. So the cool thing about that is that when they do the fermentation process to produce the alcoholic beverage, the product of that is CO2. A lot of CO2, and that means they have a big carbon footprint. But with this technology, that in principle could be utilized to take that waste CO2 and convert it back into their product, which is ethanol, it would be in place. They have no CO2; they're just using it as a resource to produce their product. And so that's a progress that's currently going on, and we'll see whether the cost of the beer and the wine goes up because you now have nanospikes involved. But yeah, so it does work, and it works to efficiency high enough that industry is interested in it. Of course, the efficiency is not perfect. And again, the reason why it's not perfect is exactly what you mentioned, defects and other things happening. And as we progress, through the years, we'll fully be able to control it better. And in the next part, I'll tell you how we think we can control it better, down to the single atom level. But it is a scientific process. But pretty cool. The other thing is those, like I said, those carbon nanospikes that can be used to electroreduce anything, right? There's a lot of molecules that you want to reduce, such as nitrogen. And nitrogen fixation is a real hard problem in material sciences because nitrogen, triple bond is really happy to be a triple bond. It's not going to come apart. And if you want to convert nitrogen into ammonia for fertilizer to make food, which is pretty important to us, you got to do something about that. And the way they do it now is a Haber-Bosch process, which is stream temperature, stream pressure, very energetically and efficient process. But we envisioned that, well, we should be able to reduce nitrogen because of this electric field effect. And indeed, that is the case. You can do the same thing, bubble in nitrogen gas, and then you can generate ammonia at a reasonable efficiency. It's not going to replace the Haber-Bosch process now, but it's just like you said, it's a step, and if we can fully understand what all is going on in terms of the defects and how we control them, it has a good chance. That hasn't been licensed off yet, as opposed to the CO2 reduction, but it's a fairly exciting advance.
Well, very cool. Thank you.
Any other questions? Because we're about at a reasonable time to break, unless there's any further questions. And then, like I said, the next part may be a little longer because I'm introducing the concept of artificial intelligence and machine learning into the process of feedback and control. Well, if anybody has questions, and I can send the email or put them in the chat. I'm going to leave this on while we take a lunch break, and we can get back to them when we come back at 1:30.
All right, great. Thank you, Dr. Sumpter.
Well, all right. Thanks, everybody. See you at 1:30.
All right, take care.
Thanks, everybody, for coming back for part 2. In the first part, I'll summarize a little bit of what we did briefly and tell you a little bit about what we can get to in part 2. Seems like my slide doesn't want to move. Okay. So in the first part, we talked mainly about everything from atoms all the way up to the continuum scale, and went over different types of computational approaches, mainly resting in the theory of classical mechanics to study things related to dynamics and structure and mechanical deformations. In the second part, I'm going to focus more on the electronic and atomistic scale, where quantum mechanics becomes important. I left it off where there was an example that if you treated the process quantum mechanically, you saw a very different result than if you treated it classically. And this is true to the largest as much of catalysis and chemistry overall. So I'll spend a little time talking about these methods and how we go about formulating and solving some of these more complicated differential equations on the computer. As I mentioned earlier, you don't have to write all the software to do these things yourself. I mean, certainly one can do that. But there's a large number of software tools and computational science tools available out there that treats quantum chemistry and quantum physics, ranging from tight binding to full quantum calculations, and also the emergence of a lot of tools that are very useful as surrogates for these models or as techniques to do analysis of data in a very efficient way, such as machine learning and agent-based modeling. These together provide a really beautiful capability to study very complicated phenomena, even phenomena that is fully quantum in nature, but also phenomena that has strong correlation that is not quantum in nature, such as in soft matter and active matter. putting those things together with experiment is made available and capable these days with very fast data analytics techniques, specifically utilizing the capabilities that rest in the class of machine learning approaches. So I'm going to talk a little bit about how they put the work together and what you can do by working together with these pieces, from the algorithms to the computers to the data analytics. Just a reminder, the role of theory modeling simulation is to develop an understanding of what's going on, to show that the miracle is actually rational. And so we'll kick it off with looking at how do we study the subatomic particles such as electrons and nuclei. The approach that is utilized to do that is the quantum theory, which is represented in a fairly nice linear partial differential equation that it describes a wave function, which gives you probability of the positions and the probability of the velocities of all the particles in the system. You need to determine that wave function, which is what quantum chemistry and quantum physics works at. And then you need to solve this horrendous partial differential equation. And all the elements that define the R's are now not atoms, but they are electrons and nuclei. So, if you have a single atom, you can have many, many electrons and many, many nuclei. But if you have many atoms, you'll have a lot more electrons and nuclei than you would ever imagine having in a classical system. So this is the hard part, but we know what we have to do. We need to solve this equation. This equation looks pretty simple, but it's pretty complicated because there are things coupled, and the dimensionality is enormous. So the time-dependent Schrodinger's equation, which is what I showed just before, is shown at the top. What we typically do is try to simplify that a little bit, and what we can say is that the positions of the nuclei, which are the atom positions, are moving much slower than the positions of the electrons, because electrons are very light and they move very fast. So we can do something called the Born-Oppenheimer separation approximation and remove out and separate those two pieces and just calculate the nuclei piece in one off and solve for the electronic piece. We can also say, well, we just want to look at structure. We don't want to look at time-dependent processes. And it can remove the time. Then you end up with a simplified equation, which is a stationary Schrodinger equation. And then you don't have to solve the nuclear piece. We're just going to solve for the electronic part. That being said, it looks better, but when you start cranking out the analytical solutions, you find that you quickly can't do it for much more than 2 to 3 bytes, 3 electrons, which means, well, that's at the hydrogen atom or hydrogen molecule, and we certainly want to study more than hydrogen molecules. So we need to do something more than analytical solutions, and that's where numerical approaches come in. So there's been two major paths to solving this set of equations in various different approximations. The chemists typically try to work with the wave function and come up with better and better approximations to get the wave function. Physicists typically try to develop more accurate Hamiltonians. Both are solving the Schrodinger equation and both give you results that are complementary. But there is a large set of ways to approach this. Back again, codes exist. There's some really good codes out there. This is certainly not exhaustive. I've only listed ones that we know scale well on the high-performance computing systems that I mentioned earlier on in the first part of the talk, that these codes promise to run at exaflop capacity. That means they take full use of the computer as the computers evolve from the petaflops to the exaflops, and they're part of a project. So NWKM, QMCPAC, GAMES, XALT are all codes that utilize quantum mechanics theory to give you structure and dynamics of materials at the quantum level. So, one doesn't have to develop these, they exist, and if one wants to run these calculations on really large computers, they will run on the very large computers and are supposed to be guaranteed to do so. And there's a large resource that backs these up, and all of these are free and open source codes, so you can get them. The PIs that are working on these codes are listed and are always open to suggestions and feedback. So we have the tools to solve that equation in various different levels of approximations. We have the computers that can allow us to do that. What can we do with that we couldn't have done earlier with the classical techniques? One interesting problem that both Vince and I worked on, along with experiments, was driven by a question of what happens in a chemical vapor deposition process if you add atoms that are different than the material that you're trying to synthesize. So this is a chemical vapor deposition chamber. It's just a quartz furnace that you put in a precursor material and heat it up, and there's a catalyst. In this case, it was carbon material, and we were growing carbon materials such as carbon nanotubes. And our question was, well, what if I put, say, nitrogen in there? What if I put boron in there? What if I put sulfur in it? Would the carbon nanotubes still grow? And if it grows, how does it grow, and what kind of structures would it get? And what we found from doing these electronic structure calculations, just basically molecular mechanics version, but in the quantum mechanical regime, what would happen if you put a nitrogen in versus a boron versus a sulfur? This shows the energies of where the atom prefers to set. And one can see that nitrogen prefers to set on a positive curvature, and while the boron prefers to set at a negative curvature, energetically more stable. And therefore, as the carbon nanotubes start to grow, if there's a nitrogen in there, they'll grow and close that growth off, and you'll get shorter tubes. But if there's a boron in there, it'll change the direction of the growth, and you get this elbow. And that was pretty exciting, because if you could get this elbow, you could keep growing the tube, and in principle, grow some three-dimensional interconnected monolithic structure. And nobody had seen that before from the carbon nanotube growth. But in collaboration with Mauricio Terrones, who's now at Penn State, and Panuco Aigen, who's at Rice, we're actually able to realize that experimentally. And you can see here in this image right here that indeed, when they put boron-containing elements inside of this chamber, that the carbon tubes grew and formed these elbows, just as one would expect from theoretical calculations. And if you run that chemical vapor deposition chamber long enough, you could imagine this fully intertwining and generating this three-dimensional interconnected structure like this versus a typical linear array that you would get without the boron. Now that gave a concept that, well, that could be a three-dimensional electrode for a battery. But the clever graduate students said, well, you know, that might be a good electrode for a battery, so you maximize the surface area for the ion to intercalate. But it also, you know, these carbon nanotubes are really tiny, 10 to 20 nanometers in diameter. So most of the space here is just empty space, it's just air. So this is all carbon, or mainly carbon. There's some catalyst in it. This seems to be a system that should look like and act like a sponge, because it's mostly air, so I should be able to compress it, shown over here, and it should reduce its size like a sponge, and then release it, and it should return to its size. Indeed, that happens. Then the student said, well, this is carbon likes, but it doesn't like water. So this could be an amazing actual sponge for oil. And so this over here on the right is an actual demonstration starting from some computational discovery to the synthesis and to the actual application, where this monolithic structure that was grown in the CVD chamber is placed into a slurry and oil. Now, because it loves oil and it's water, it'll suck up the oil and is repelled by the water. So that's indeed what happens, sucks up all the oil. And now you can just squeeze the oil out and recover it, or burn it and get the energy. Of course, burning makes the temperature hot, but the carbon nanotubes are incredibly thermally resistant, so it actually can be cycled back and forth many, many times and is highly robust. So this is a new way of developing a new material technology that could be used to clean up oil spills in seawater, starting based upon ideas and concepts and a full realization through quantum calculations to experimental synthesis and demonstration. Pretty neat. Another example, moving from structure here that ends up to having a really nice technology. So, well, what about charge transfer in our devices due to contact interfaces and transfer of electrons? Now, if we're going to look at charge transfer, we have to consider the famous time-dependent Schrodinger equation versus the independent one that we just talked about in the oil spill case. This is a little harder because now you have the element of solving that differential equation in time. But there's ways of doing that, and there's quite a few. Some are a little more efficient than others. And we took a special approach because we were really wanting to look at charge at interfaces and during collisions. So this this is an example of a study showing a buckyball that's neutral here on the left, and a buckyball that has 2 electrons removed, so it's a +2 cation of C60. These are close enough together that already the absence of electrons on this buckyball is pulling and polarizing the electrons on this buckyball, shown here with the light green as an excess of electrons and the dark blue is depletion of electrons. So as these things are collided together, and there's reasons that you want to accelerate these for purposes of propelling and also other chemistries, we wanted to see when the charge transfer happens and how it equilibrates. And in order to do that, of course, we have to solve the actual Schrodinger equation for the electron dynamics. And this is just an example of showing that we can do that. As they collide, there's a transfer of the electron. It's really fast, sorry about that. The time scale for this is femtoseconds. So we start off, it's polarized. As it gets closer, you'll see the dark blue over here starts to collect the light green, which is a charge. So it's transferring a single electron, and actually a single electron is already transferred there before they even collide. They collide, they repel, and then they'll equilibrate the 2 cations, a C60 plus over here and a C60 plus over here after it fully equilibrates. So we're able to solve that time-dependent Schrodinger equation and study these complicated processes of interfacial interactions, charge transfer in real systems. So that was pretty exciting. The way we did that is solved for the nuclei dynamics using a classical trajectory, but the forces are determined from the electronic structure calculations. And then we propagate the electron dynamics, the charge transfer part, how the electrons move around using a density matrix. And we can calculate those pieces with really complicated quantities, such as beyond density function theory, or we can do it with a tight binding calculation, which means if we do it with a tight binding, we can do a very large system. So we're able to do that for thousands and millions of atoms, and with this approach, which is founded in hydrodynamics, the Liouville von Neumann equation, which is this equation here. So it gives us a fairly good speed up and almost on the order of n scaling, which means we can do very large systems fully quantum mechanically and fully treating the time-dependent Schrodinger equation. So that was pretty exciting. So sort of completed the full gamut of length and time scales that we can do simulations on from the bottom up, or I started from the top down actually, from the atoms and electrons all the way up to the continuum scale. And this multiscale approach is typically what people use. Again, there is great bonuses because it's not all about just treating chemistry and materials and physics. It also allows us to look at a gamut of different complex engineering problems as well as other types of science problems. So it's a pretty enabling set of approaches in this suite of techniques that currently exist and are also continue to develop and improve. So what can you do? These methods really can provide a real strong foundation for understanding and predicting properties and processes, such as trying to understand quantum materials, which is a new realm of materials and materials processes. We would like to be able to master that, and there's reasons that you want to master that. And it's not all just quantum computing, but also quantum sensing, sensing beyond the classical limit, and also communications, new regime of communications and security. So there's a lot of reasons we need to understand that in great detail. We can understand and tailor excitations and transport. Excited states and materials are important. So it's photovoltaics. Also, transport is incredibly important for in batteries and various other processes. Functionalities and interfaces, we need a whole new regime and a new generation of catalytic processes. I talked a little bit about carbon nanospikes and electrocatalysts. We need more of these types of discoveries to allow us to generate the types of chemistries and materials that we're going to need for the next generations of technologies. And we need to be able to do it in a very efficient, energy efficient fashion. So these techniques that we've been talking about allow us to look at that. And finally, understanding and controlling what kinds of defects and what kind of dopants are in materials and where they are in the materials could be revolutionary to the next generation of structural and functional materials. So I'm going to talk a little bit about these last two, and if there's any questions about this, I'd be happy to address them. So just a quick perspective in terms of defects and control. In our general quest on the science technology area to meet national needs and the next generation of technology, we're really reaching directly to we're going down to the bottom. And Feynman also had said stuff about what if you could control atoms individually, do anything, and that may be true, and we're getting to the level where we can do that. Things that come out of controlling atoms and dopants at the single atom level is things in the quantum information sciences, new efficiencies in multifunctional materials and energy storage, conversion, and transmission. So as we're moving down in our science is really transforming our understanding and our ability to have these big impacts across both physical, chemical, and material sciences, as well as biological sciences. The goal is always to be able to predictably design our materials and chemical processes, and this idea of understanding through control and control through understanding is really relevant in this quest to generate that technology. So we have always known that manipulating atoms and defects makes materials change, and even way back to several hundreds of years to thousands of years ago, people forged steel by putting defects into it. That made the steel much stronger. That is still relevant, but the difference between forging it at the macro scale, as in the old Titan days, and what we can do now in preparation of ultra strong materials, is that we can reach down and control individual single atom defects. And if we can start controlling those, that means we know where they are exactly. And then we can actually begin with that control, develop this correlation between the structure and the defects and the properties. When you do it this way, you sort of get a random selection of different things. It's hard to form a structure property very simply. So now we have hope if we can control those defects. And I'll show you that we can indeed control those defects. So what we want to do is basically control, understand, and predict those defects, and use those defects to lead to new developments in terms of understanding, as well as developing materials with directed properties. So the first step in this is being able to see the defects. If you can see it, you sort of is the first step in feeling comfortable and understanding. There's many ways of looking at materials. Some of the best ones are in real space, and these are scanning probe and electron microscopies. There's a whole large suite of possible ways of doing that, and I'll go over some of the tools that are there for that. There's also a variety of scattering technologies, neutrons and X-rays to allow us to look at some things in reciprocal space, which is provides us additional information. So we have ways of looking at materials at the atomic level all the way up to the macro scale, and that gives us looking at things not just a picture, although it does make a beautiful picture. From that picture, you can actually get the bond lengths, the bond angles, the torsion angles. As I mentioned, the carbon nanospecs. That's how we got the more realistic models, is looking at this electron microscope. And from the bond lengths and the bond angles, you can also infer various things about configurations and therefore about phase changes and properties just directly from the image. So it's a very powerful technique. Tools that we have currently that allows us to see atoms. There's a whole suite of them: electron microscopies, transmission electron microscopy, scanning transmission electron microscopy. There's a whole suite of tools. These are getting bigger, or not bigger, better and better, sub-angstrom resolution already, so we can actually see atoms and below atoms. There's new tools that are ultra or low temperature scanning tunneling microscopies, allows us to probe quantum phenomena directly. And chemical spectroscopies that are based upon helium ion microscopes or time-of-flight systems that allow us not only to see things and image things, but to get the actual composition directly. So these are powerful tools. They all exist, and each one can be integrated directly in some sense with a theoretical calculation or a simulation, which makes it a very powerful approach. Just briefly to go over some pretty exciting new developments that have came along recently. I'll start off by talking about what one can do when they put all this together. So I'm first going to start with just some neutron scattering. So we're starting with bulk scale materials at this point, but we're going to do this at the same time as we do the calculations, and then the data from the experiments are going to be streaming across to the calculations and vice versa. Whereas we'll make a measurement on a very simple material called barium titanate, which has an nanoferromagnetic and ferromagnetic instabilities in it due to some non-harmonic interactions. So we make the calculations and we can predict the structures that one should see from the scattering, and we can compare it while we're doing an experiment to what you get from the scattering. And when this was done, it turned out that we found in the calculations immediately that there was a strong anharmonic or non-harmonic effect that affected this interferomagnetic stability. But the experiment didn't see it. And the reason why the experiment didn't see it is because the alignment of the sample and the beam of this inelastic neutron scattering spectrometer was not correct for the phenomena that is seen. So this calculation guided the experiments to realign the scattering, and when they realigned it, they were able to see this phenomenon. So if they had not had the simulation happen at the same time and the streaming of the data back and forth, they would have missed it. And then they said, well, it has nothing to do with this instability. But the fact is, it does, and this was discovered because of this ability to stream this data back and forth and do the calculations during the experiment. So that's pretty exciting. What that means is, well, now we're sort of transitioning. I talked a lot about, we make some things, we characterize it, we do theory and simulation, understand it. Now we're doing things at the same time. We're doing synthesis and characterization and theory and simulation at the same time with real feedback. And that's a powerful approach. And that's enabled through our ability to do those calculations really quickly. All these approaches that we talked about and developed in high performance computing enables that. And with all that comes a lot of data and a lot of need to do really quick data analytics. And so what I'm going to do is now talk about how we can do the data analytics on the fly with streaming experimental data and streaming theoretical and computational data in order to feed back to the experiments to guide it toward new discoveries or to the synthesis of the materials. So again, it's all about control through understanding and understanding through control. So looking at atoms, the first thing typically we do to see an atom is a scanning transmission electron microscope. That's shown here on the left. These are fairly large systems. You can see it's actually on a ladder. The more powerful ones are even bigger. But they basically have a very focused accelerated beam of electrons. These beam accelerated down to a couple angstroms in the apex. Passes that through a thin sample, and then that is transmitted to a detector, which records the position of the atoms. So with a material, you can actually, such as graphene, that's very thin. You can put it under the electron microscope, and you can actually see the individual atoms or the individual defects. Sorry, my son is playing some game. So you can see here in the middle that the carbon atoms are shown a little light or darker, and these dopant atoms, which are tungsten, it turns out, are shown a little brighter, and that's because this thing has Z contrast, where Z is the element number, and it's inversely proportional to that. So the brighter atoms, there will be the heavier atoms, and the darker atoms will be the lighter atoms. So we can get a little bit of information, not only on the position, but also whether there's different types of atoms, and we can sometimes derive a little bit of understanding about which type of atom it is through another technique called electron energy loss spectroscopy. So one of the things we noticed doing experiments is that when we were looking at the region between a crystalline domain, this is just a very nice, beautiful crystalline aniline resolved domain, and an amorphous domain, and we were scanning across that domain, that as the electron beam scanned across it, we noticed that the crystalline domain grew in the direction of the electron beam scan. And that could be actually drawn out to any sort of length scale into this amorphous domain. So what we see is, well, that's interesting. And one of the things I think is a cool quote is, the most exciting phrase in science is not eureka, but, well, that's weird, or that's funny. Why did it do that? And we were able to actually do the same thing with heterogeneous and different types of materials, so barium titanate, unstrut titanate. There's reasons you want to be able to do that. By just focusing electron beam at an amorphous area and crystallizing on demand single, atomistically precise structures. Just to show you how you can do that with feedback and control the direction and the growth of this crystallization process. As you see, as it propagates, we're just moving the electron beam across that interface and directly controlling the crystallization growth processes at a single lattice scale. These are angstrom scales that we're controlling that. So that's pretty cool. Again, that means that you can use the electron beam to manipulate the phase change of materials. But what can you also use that electron beam to move the atoms? So the answer is yes. So we can image the material. So shown here is the electron beam. This is the cartoon. This is graphene. There's some silicon on the graphene over here on the edge that we put on. And it's also in this image up here on the left, which is a real experimental image of the microscope. Pristine graphene domain, a little bit of silicon. We can focus that electron beam on a region and hold it there. And if we do that, it actually removes it. So this is the model, and this is the actual reality of the experiment. So the electron beam can not only grow crystal structures and by introducing phase changes, it can knock atoms out. They can also clearly image the atoms quite nicely at the atomic scale. What if we put the electron beam over here on the silicon atoms and raster it at a rate that we don't knock the atom away, but just push the atom? Can we push that atom over into that hole? And now we created a new material. And indeed, we were able to actually push that atom over in the hole in reality. So that means that we can actually sculpt our atoms. And this is a real-time dynamics, an experimental image of moving an atom on a surface. We can manipulate them and put them where we want to. We can make dimers, we make trimers, we make tetramers. We can make lots of different structures out of different types of atoms. Now that's a pretty powerful capability, because as I mentioned, we are directly manipulating single atoms, moving them where we want them exactly, which opens up a lot of possibilities. That being said, just doing it trial and error kind of is not that satisfying. We do want to minimize all the surprises. You don't want your quantum computer broken in every way possible at the same time. We want to understand and control things better than that. So how does the electron beam actually do the actual the actual motion generation? Because typically the energies are maybe not as high as you might think would be needed to pop out a carbon atom in a graphene lattice. So that's where the calculations and theory comes into play. We have a model which says that we have an accelerated electron beam that impinges onto a graphene surface. And so we can do a calculation that lets us look into what sort of energy landscape these carbon atoms see before and after an electron beam is passed through. And if you look before, for example, we have a very large barrier for different types of chemical processes. This is not necessarily a moving atom, but it is a chemical process. And in one case, when there's no electron beam, the energetics to move something across a barrier requires almost 2 electron volts, which is really very high energy. Now, if we pass electron beam through or near that position, that barrier is lowered by an order of magnitude, which means the process can proceed under that excitation and cause that type of motion. And we can map out the barriers and the transition rates as a function of where that electron beam is put, and see where it is best to focus the electron beam in order to, say, move a silicon or atom to a particular position in a lattice. So this, between the experiments and the theory, now we have a way of sort of directly manipulating atoms in a lattice and putting different atoms in that lattice at the atomic scale with really good control. And that's kind of exciting about that is the electron beam is not the same as a photon, which now we are able to use electron beam to induce chemistry. Typically, we're not doing that. Typically, the path for that was lasers. But now this opens up a new realm of possible ways of doing chemistry with these convergent electron beams, and we're pretty excited about that. So what we have is a way to move our atoms in an electron beam or an ion beam. It doesn't really matter if it's electrons. Electrons work quite well. We have microscopes for it. But even with the theoretical input and feedback with experiments, it still is a little bit of a trial and error approach. And to actually build a material that is relevant to a device, you need to do a lot of atoms, and you need to move a lot of atoms. So it's not practical to just keep trying and experimentally run the microscope until you get a result. Because when you're trying to move an atom like this one over here in the right side to a position, just putting an electron beam, as I said, on the atom itself is not the way to do it. You have to put it, it's not quite intuitive. Theory can tell you where to put it, but then you have to do the calculation again and again and again. So what we need is a feedback loop that allows us to control the microscope. And then we can put controls on the microscope. It's pretty easy to put scan coils on it, control the X and Y, Z position, and also we can control the dose and exposure time quite nicely. And we can put that together in a feedback loop. But we need to be able to do that in real time as the data is streaming and with the ability to process that. So right now, when we look at what we capture data-wise, it's about 400 gigabytes per second of data that's coming off of this instrument. In order to process that, and move that, that's an incredible challenge. And we need to be able to do that, and coupled with the theory and calculations on the fly during this experiment, which the experiment's taking, seconds to minutes. So it's a huge amount of data. So that's where data becomes a challenge, but also it becomes an opportunity because we can deal with it, we can feed back, and then we can move these atoms precisely every time where we want them, and we could have a possibility to scale this up. So data science is not new. Statistics have been around for many centuries. But the concept of machine learning and the applications of these two materials is a little bit newer. It's not so new in terms of Google and Microsoft and Facebook. They've been using these techniques a long time to make recommendations. They also use them to do self-driving cars, robotics. They do work. And so, you know, our question is, well, why can't we just use these tools to sort of complement our approach on electron microscopy to grab the data and analyze that data and automatically feed back to the microscope so that it can do the next thing that is the correct thing. So sort of looking to automating our experimental tools. So, you know, as I mentioned, it's not new. Long time ago, it's not that long time ago, in the 90s or late 80s, the idea of neural networks became popular again, and it was clear that these techniques allowed one to do a lot of connections between structure and properties, and even some design of experiments and some design of materials. So what we have is an experimental result that we know we can sort of understand. We can move things around. We can drill holes and put things in those holes on demand to some extent. And what we want is to understand the physics that underlie that, and how we get there is this idea of putting in these machine learning and data analytics tools to allow us to feedback and directly control and repeatedly be able to produce the same type of result. So what can machine learning do for atomically resolved imaging? Here's again an image of an electron microscope at a fairly low acceleration, so the image is kind of blurry. But we can sharpen that up through different filters and different approaches. But typically, what that means, if you have, say, 1 million of these images, it's, you know, that's a slow process. It's not fully automated. It's manual. If you're doing that one snapshot at a time and you have 1 million of these, it's going to take you a while. And each person does it slightly different, so it's a little prone to error. So what we want to be able to do is use machine learning tools to take all that noise out of the system, automatically sharpen this image and automatically determine all the positions of the atoms. And if you do that, as I mentioned, you know, it's not just the image anymore, but it provides you a lot of information about defects, dynamics, and all types of properties. So when we do this, this is just a simple example of actual convolutional neural network being applied to a real horribly resolved image of a graphene system with a hole and some silicon atoms dancing around that hole. You can see there's something happening. You can't see the atoms. You can see blurs. This convolutional neural network can denoise that and sharpen it. And actually, over here on the right is the convolutional neural network's results, showing every single atom. You can see it's hexagonal lattice, so it is graphene, or you couldn't see it over here at all. And you can see the positions of those green guys correlates very well with the positions of these white guys. So we're actually able to use this approach to fully automate and help incredibly resolve and understand exactly where the atoms are and how the motion is occurring in the real experimental image. So this does work, and it works quite well, and it can correct for many artifacts. With that, now we can say, okay, so I can see atoms, I can see defects, and the neural network can help resolve that at different energies, which means I can start moving things and controlling things really precisely. But also, if I know the symmetry of the material, I could start specifying the actual what type of defect. So this is just a case of a molybdenum disulfide system that's doped with tungsten. So the brighter atoms are the tungsten atoms, the darker ones are the molybdenum and the sulfur. and we're exposing an electron beam, so we're knocking atoms around and we're moving some of the tungsten around. The tungsten is aggregating. And we're forming all sorts of types of defects on purpose because we're wanting to let the neural network learn the different types of defect types. And it turns out that one can classify those quite precisely. And there's about 5 different types shown down here. There's one case where there's a vacancy that is caused by knocking it out with the electron beam. Sulfur is gone. There's another case where there's a tungsten atom just sitting on top of the surface. There's a case where there's a different type of vacancy caused by knockoff of the sulfur. And then there's a case where there's actual tungsten vacancy that is caused by the knock-on energy of the electron beam. And finally, there's a multiple sulfur vacancy case. And so these are colored here, and as the experiment is occurring in real time, we're able to classify all of those and track them. So if you look at that, it's a lot of stuff happening over here on the right that correlates directly with what's happening on the left. And we can classify each of the defect types that happen during that actual experiment. And then if we can do that, then we can learn a lot about the physics of defect formation, defect evolution, defect creation, and defect dynamics, which is we don't understand at this point. So we can track them as shown here. Some of these defects don't move much. Some of them have a very, very mobile behavior, such as sulfur defects. We get diffusion coefficients and start understanding the full dynamics and full physics that underlie this process. So pretty neat, pretty exciting. We can just push that data directly into a database, and we've done that for the defects. And then we can augment that with calculations. So we can take those well-characterized defects and submit them to electronic structure calculations and simulate, say, scanning tunneling microscopy for all those defects. And then you have a database that not only has how the defects look under the electron microscope, but also how the defects would look under other types of microscopy, such as scanning transmission or scanning tunneling microscopy. This has been done and it works very well. If you're interested in reading more, there's a pub down here that I would recommend you taking a quick look at. So with that, I showed that these tools are incredibly useful and will enable some pretty neat advances. I only talked about the microscopy so far, but as I mentioned, we did do some neutron experiments, but you can also look at X-rays and photons to manipulate and inject energy into materials. And there's no reason why we can't use those as modalities to image and manipulate the materials. But this means that, now we have multiple different sources of data, and we need to apply those data analysis and machine learning tools across a gamut of different sources, which means there's got to be some sort of common data format and common metadata information provided in order for this to be piped over to a machine learning or an AI technique in order to allow us to control these different sources of energy to manipulate these materials. And that's an ongoing process. So, being able to do that is fairly challenging, but there is some hope and reason to believe that we will be able to do that for multiple different modalities of experiments and calculations at the same time, and translate some of these technologies across different facets. So right now, as I mentioned, what we have done is as we are progressing from our 10,000 frames a second in our detectors to 100,000 frames a second in these electron microscope and X-ray scattering detectors, which means we have this big data. This is not only relevant to electron and neutrons and X-rays, but also 3D printing and other types of technologies. Using this approach of integrated theory modeling simulation with these data analytics and machine learning tools, as applied to high performance computing, we're able to actually take that information on the fly and utilize it to not only accelerate and improve our imaging, as I showed already, but to start self-driving feedback and say, here's a region I really want to have a tungsten atom sitting, make it so. So that's actually coming along quite well. We have these real-time models in the experiment loops, and we're starting to be able to go in the backwards direction. So asking a question about if I want to produce a material that has a particular melting point, a particular magnetic property, and I have these elements, how do I do it? The inverse problems, these are incredibly hard to solve, but we're making some progress there. And as I mentioned, this automatic analysis feedback loop is making great pathways toward self-driving instruments and autonomy. Finally, if you can do all this, we can start accessing a whole host of new properties and that are enabled through the materials, because we're assessing different chemical states or physical states that are typically not going to be there in our normal processing. So this really does open up a whole realm of possible exciting future technologies. With that, I would like to put a corollary. What I'm talking about here is correlating, some input to some output, where it's imaging to some process such as the defect formation, and that's called correlation. Again, as I mentioned before, structure property correlations are a powerful, powerful technique, but is correlation enough? There's something called symptom paradox. Just show you an example of that. This is the amount of cholesterol in a human as a function of the amount of exercise they do. If you look at this plot, you say, well, wait a second. If I exercise more, my cholesterol is higher. Wait a second. Is that right? That isn't right. But it's an artifact of the way we're plotting this. Now, if we plot that differently and instead show the age and plot it as a function at different age categories, now you see the more exercise you do, the less cholesterol you have. So you have to be careful. Correlation is not always enough. You need this as causal, the cause. It needs to be integrated into this. So there's a new generation of trying to be able to inject in a smart analysis and the data in order to extract a meaning and beyond correlation out of these techniques. And that's the next stage. Correlation to causation. Astronomy does that all the time. They don't really do experiments. They measure things, and they can actually come up with really sound causes. So this is not something that doesn't have a possible solution, but it is challenging, and that's sort of the stage of the next generation in the process of utilizing these tools. When we put all this together, we do believe that we can add automation to many of our experiments, even experiments including synthesis through robotic and dip pen technologies. But when you do this combinatorial dip pen type approach, where you're just taking microarrays and putting different chemicals in each one of those, and then trying to find which one is generating the best material, it's a problem because it's sort of random. We need that to be guided, and so these can be guided. Some of the expectations can be set by theory and modeling simulation, but they can also be guided by these artificial intelligence or machine learning tools, and to indicate which direction to go in that chemical space in order to get the property that you would like to get. So it's not a blind search anymore in the combinatorial space, which is basically infinite. It is a smart search, which reduces or increases the probability of having high success. So there's a lot of reason to believe that these techniques, coupled with some of the automation that I mentioned and theory, can lead to generation of a quite exciting level of transformative materials and chemical sciences in the near future. So we went through a lot of stuff today. Hard to judge if I'm going too fast or not. Probably I did. We talked a lot about theory, mainly classical and quantum theory, and when they're the best to be utilized. We also talked a little bit about experiments, the microscopies, and how those can be utilized to manipulate materials. And then we talked about simulations, which take the theories and put them on a computer, and couple those together with machine learning to derive new levels of understanding, automation, and control. This is sort of where we are now. And as I mentioned, there's a next stage, which is the artificial intelligence stage, which is a little higher level than just machine learning. That allows one to actually start making real adaptive decisions, learn from mistakes, just like we do in real life. So that's the next stage, and that's a direction that a lot of things are going currently. So just to summarize, if we understand where the atoms are and what they do, we'll understand what gives rise to all the materials properties, and also how we can control and direct that. So we have transitioned from our traditional approach, where we do things in sequence, make things, characterize them, understand them through theory and simulation, to doing it all at the same time. And that is a truly transformative advance in the sense that now we can actually control the position of the atoms in near real time, which means we'll be able to make pretty big strides in the near future in the area of generating materials with real design properties, or processes with efficiencies that are unmatched. Just to end, I want to say that there's a lot of things one can do if you can control the materials. This is a really great stress reliever out here, a fidget spinner. That's a real fidget spinner. This is a nano fidget spinner. This is actually done through a 3D process that's at the nanoscale, or at least several hundred nanoscale. It's a 2-photon polymerization technique. So anything we can CAD, we can make. So we CAD'd up a fidget spinner. So basically, what you're seeing here is the world's smallest fidget spinner, and we can actually spin it. Sighting there, it's spinning. So we're through this idea of precise control and delivery of energy, we're able to do fun things too, such as nano fidget spinners spinning coherently at the same time. So that was demoed, and actually this is moving around in a science truck across the Tennessee area that we show aspects of nanoscience and technology to students in the STEM areas. So I promised that maybe I would have time to give a quick example of how we put all that together. A lot of that was fundamental. A lot of things in the real world are applied, and we're using one of them right now, an application to talk across the internet. So I'll just give a quick example where some of these techniques can be used to solve really global scale problems. This first example is an example that is work with Procter & Gamble, who makes a large number of commodity products, including shampoos, detergents, diapers. Very large quantities of these things are utilized daily. And they have a process, and a process is highly efficient. But as time moves forward, they change their manufacturing process, and they need to understand whether that change justifies the costs that would be invested to make the change. So in this case, they were wanting to understand if one could enhance the ability to move plastic bottles through an automated system which would fill those plastic bottles with shampoo. And which is shown over here. What happens in this process that they had come up with, that would be the next generation manufacturing of this shampoo, was having a problem. The bottles themselves, which are made of plastic, was pulling a static charge, and when they pulled that static charge, they actually stuck together. And when they stuck together, this conveyor belt that was moving the bottles down to be filled jammed. So this is a really nice example of jamming behavior. And when that jams, they have to stop the conveyor belt and clean it off, and that disrupted their process in order to deliver X number of bottles per hour. If they didn't generate X bottles product per hour, they would be losing money. And of course, they don't want to lose money. So they came to us and said, can you understand how this is happening? What is causing these things to stick together? Is it a static charge? And how can we mediate that static charge without changing this process? And so, we did a lot of different studies with scanning probe microscopy to look at the static charges, do calculations to see where that static charge set, and then ask the question, well, what should we put in on this model or in the precursor, the mixes ball, to stop that static charge so this thing doesn't jam? And that was actually quite successful. And then they actually launched this technology a couple of years, I think last year in West Virginia. I think it was a $100 million effort that now is generating the next generation of plastic bottles that hold all your shampoo. Many other things that came out of this project. That was a pretty neat one that is very recent. Again, experiments were done, simulations at the coarse grain level and atomistic level and at the quantum level to understand that static charge and how the additives could be used to passivate it were done and fed back to industry. Another quick example is a small company, Vinium. I think it's in Massachusetts, but looks at additives for friction reducers. Of course, we use a lot of those for our engines in our cars and various other aspects that are quite important to society. And they had a couple of different friction reducers that they had found, and they were wanting to understand which one might be the best at reducing friction under the conditions that they were interested in. So we were able to do some simulations to understand what happens to these different additives under the friction conditions, which are around 3 gigapascal and around 120 degrees C in the process that they're looking at. One immediately sees that when you have this trimer in under that condition, it forms structures that are very different than when you have the dimer under those conditions. And what happens if you look at these structures, it turns out that these structures kind of look like particles of molybdenum disulfide. Molybdenum disulfide itself is an amazing friction reducer. So theoretically, it looks that if you use this trimer versus this dimer, that you should have a incredibly enhanced version of an additive to reduce friction, which is the goal. And indeed, that turns out to be the case. And we experimentally have been able to validate that and feed that back to the company, who is now wanting to say, okay, what could be a better one? Can you come up and verse design something that's better than this trimer? So that's a process, again, that simulations and modeling can help resolve. Anyway, so that's sort of some of the story I had for this second part. I think we have a little time for questions, and I'd like to thank everybody for hanging in there. I know it's a lot of information, and hopefully have any questions, you ask them or send me email at some point. But I am finished for the talking part. I see one question in the chat. Have you used Bohmian trajectories for these? Yeah, absolutely. So that's a very efficient approach to do mixed classical quantum calculation. In fact, we had developed a suite of Bohmian calculations, and where we use that is to ask the question, what happens when I put a isotope into a material? So I say substitute a hydrogen atom for a deuterium atom. Electronically, the orbitals shouldn't change, right? Because it has the same number of electrons, but dynamically it changes because you have a nuclei that has a neutron in it, so it's heavier. So we use the Bohmian approach to treat quantum mechanically the nuclear part of the wave function, and then treated the other part with the classical electronics, and found that it not only does the mass change the vibrational frequency, but it also changes the electron phonon coupling, which affects all sorts of physical properties, turns out. And then finally, it feeds back to the actual structure properties. So, isotopic substitution is a great labeler, but it also changes the material at the atomic level and affects the properties. So, the Bohmian approach was used to study that. Let's see if there's any more. I don't think there's any. Quantum phenomena are not necessarily a priori predictable. So, the fact is that materials are quantum, okay? And, what the degree that the quantum effects modulate the properties is a question. Sometimes it doesn't really affect it that much, and we can get away with classical simulations. But the fact is, if you do quantum simulations, that's the best thing you can do, always. The problem is you can't always do it because the processes that you're studying are not commensurate with the time or the length scales you could treat. So, light atoms and tunneling phenomena happen. If you're a really high energy, probably the quantum's not such a big deal. But there is energy regime where quantum becomes really important. That's sort of where we are in the quantum materials regime. The reason that those things are so fragile is they're at very low energy regimes. So that's a condensed matter system, the topological quantum materials. So yeah. We've seen electron beams can move atoms. Are we able to model this classically or semi-classically? So yeah, of course you can do that. The problem is if the electron beam is putting that system in an excited state, then you need to put some information into the classical, or particularly the semi-classical approach about that excited state. So there's something called surface hopping. It's not a quantum approach, it's actually a classical approach. So absolutely you can do that. And we're looking at that. Again, it's always best to try to start with something that gives you a result that's calibrated to some extent, and then try to go back and reduce it to something simpler when you're understanding and learning. So that's the approach we took. We took the more full quantum approach, and certainly one can go back to a classical and semi-classical approach, but there's always approximations that you need to take into account in those approaches. So you need to calibrate things back, and so absolutely you can use classical and semi-classical. So answer that. Okay. I don't see any other questions on the chat. I mean, I think people can actually just speak up or anytime they want, but I'm not 100% sure. Okay, well, we're done just a little early, which I was hoping to get done about 15 minutes early, which we are. I'm happy to answer any questions that you have. If you want to email me or email Joel or Vincent, and they can let me know. Also, I encourage you to, look into Oak Ridge National Laboratory and opportunities to visit. And once we get past the virus episodes that we have right now and the COVID, but even if one is considering to do research in computation theory and modeling, one can even do that off-site. You don't actually have to come on-site, but obviously Oak Ridge is a beautiful place with a lot of opportunities, and I would encourage you to take a look. And earlier on in the first part of the talk, I had given the websites that you can look up. And one of the websites is specifically for doing internships and visits through the Oak Ridge Institute of Science and Engineering at Oak Ridge National Laboratory. So I encourage you to take a look and shoot me email at any time, and be happy to answer questions or try to help direct you to a source that can answer the question.
Awesome. Thank you so much, Doc.